Okay, great. Thanks so much for the invite to speak at this workshop. It looks like there's going to be a lot of exciting papers, so I'm going to stay for as much as I can until it gets very late my time. Um, so today I'm talking about theoretical models for opinion polarization via local edge dynamics. This is work that actually appeared at this Wisdom this year, and it's joint work with my student Adam Lekovics and my other student Nikita Bala. So yeah, what am I talking about today? So our main sort of focus on this work is we propose a really simple theoretical model. Oh, I guess I should say that I don't know exactly how it works in the room, but feel free to interrupt with questions during the talk. I'm totally fine with that. I don't see hands, but feel free if there are hands, someone can call on them and interrupt me. So the main contribution is that we propose a very simple theoretical model for network and opinion coevolution. So how do the links in a social network affect the development of people's opinions? And in turn, how do people's opinions affect the links in a social network? And how do these sort of feed back on each other to create phenomenon like polarization? Yeah, so we look at basically how do node opinions drive the addition and deletion of edges on a social network, and how do these edge modifications drive opinion evolution? And we use our very simple theoretical model to study the role of phenomenon like confirmation bias and recommender systems in driving opinion polarization and filter bubble formation in social networks. So just as a disclaimer before I get started, the model I'm going to present to you is highly stylized and theoretical. And this is sort of on purpose. I'm a theoretical computer scientist. We like these really simple models that we can try to get our hands around theoretically. So you should think about this model in the same spirit as well-known models of opinion dynamics or social network graphs like de Groot learning or Fredkin-Johnson dynamics, preferential attachment models, stochastic block models. We know that none of these models is even close to representing the real world with much fidelity, but nevertheless, they're useful models to study to sort of try to get our hands around what's happening in the real world theoretically. So I just want to give that disclaimer before I start. And obviously, like trying to make the model more realistic or validate it with more real world data is going to be a really interesting follow-up work direction. Okay, and so I also wanted to say that our work, I won't do too much review of literature here, but our work fits into a really broad literature in recent years that studies opinion polarization and filter bubble formation. So there's been a lot of really nice work that looks at how does the structure of a social network itself lead to opinion polarization under different opinion dynamics models. And often that leads to asking the question of how can we rewire edges in the social network to do things like limit opinion polarization, or maybe how can we rewire edges to make the network as polarized as possible if we're an adversary. So there's been a lot of really nice work along that line. I've had some work in that direction. There's also been, it's going to be very related, a lot of work on the effect of recommendation systems on network structure. So for example, if I have a social network that's doing recommendations based on similarity of interest, or maybe based on similarity of friends, like friend-to-friend recommendations, there's been a lot of work looking at how does this drive the network structure? And then you can ask, of course, in turn, how does that network structure drive opinions via opinion dynamics? What we're really interested in is something that I think has been studied a bit less, but there has been significant prior work, which is the coevolution of networks and opinions. So how does this feedback cycle happen where the opinions affect the network and the network affects the opinions and vice versa? There's been some work in this going back, at least from what I know, to the early 2000s in the statistical physics community, proposing really simple models for opinion and network coevolution. And there's been some other recent work which studies models that are somewhat similar to ours, and sometimes has some similar conclusions. Okay, so with that, I'm just going to tell you about this simple theoretical model for opinion and network coevolution. So our model is going to be built on an underlying opinion dynamics model, a popular opinion dynamics model called the Fredkin-Johnson model. So in this model, I have n individuals, and they're represented by the nodes in a graph. And for simplicity, I'm just going to assume this is undirected, unweighted graph. And each node actually has two opinions. Every node has an innate opinion denoted by SI, which is sort of, you can think of as that's like their opinion if they had no social influence. That's like sort of their innate opinion on some issue. And we're always going to think about unidimensional opinions, just numbers on the real line. And I'll actually just always think about them as being numbers between -1 and 1. Every node also has an expressed opinion, which is also a number between -1 and 1. And initially, the expressed opinion is equal to the innate opinion. So this is basically their opinion under social influence. And before their influence at all, it's just equal to their innate opinion. So at every time step of the Fredkin-Johnson model, a node's expressed opinion is obtained by a very simple averaging process. They take an average of their innate opinion plus the expressed opinions that they see at the neighboring nodes. They just literally take a simple average of those, and that's their new expressed opinion. So their expressed opinion takes into account their innate like thoughts on the issue, but also it's significantly affected by the expressed opinions of their neighbors. And there's lots of variants on this model where this is like a weighted average, and there's multidimensional opinions, but I'm just going to stick to the really simple variant today. Okay, any questions on that? Okay. So just to give you a sense of what this looks like, let's say I have just a 3-node social network, and the darkness of the node is its opinion. So this node down here has sort of like a opinion on one side, and then these other 2 nodes have an opinion on the other end of the spectrum. In the Fredkin-Johnson model, what will happen in the first step is that the nodes will sort of average their opinion with the expressed opinions of their neighbors, and they'll all converge a bit more to the center. Actually, this node that had an initial innate opinion being kind of a lighter color actually gets a darker color because it's averaging with 2 neighbors that had very dark colored innate opinions. Then they'll repeat this process. They'll average again, and they'll average again. And eventually this will converge to an equilibrium where the nodes have taken into account the opinions of their neighbors, but also their innate opinion. So this node V2 has a somewhat lighter color because its innate opinion is lighter, but it's much, much closer to the mean because it's being averaged with its 2 neighbors. Okay, so that's just an example of the Fredkin-Johnson model. And at equilibrium, there's like a very simple expression. It doesn't matter much where this comes from, but one thing that's nice about the Fredkin-Johnson model is there's simple linear algebraic expression for the expressed opinions in terms of the innate opinions. They're basically, you apply a linear transformation to the innate opinion. So if I have a vector of innate opinions, S, so I have this vector like S1, S2, S3, and I want to transform it to the expressed opinions, Z1, Z2, Z3, I just multiply it by the Laplacian of the network plus the identity inverse. And you can check that this is sort of the fixed point of this opinion averaging iteration. Okay, so that's the opinion dynamics model. In this model, we're going to use a couple very simple metrics of polarization, which aren't necessarily the most realistic or I guess best metrics of polarization, but they're metrics that have really natural linear algebraic forms in the Fredkin-Johnson model. And so we're going to be able to analyze them theoretically. So what we're going to call the polarization is simply going to be the variance of the expressed opinions in the network. The higher the variance of those opinions, the more polarized the opinions are, the further they are away from the mean. And I'm always going to assume, by the way, that my opinions are mean 0. So by variance, I just mean the L2 norm of the expressed opinion vector, which if we use the Fredkin-Johnson equilibrium, this is just a quadratic form of the innate opinions over the Laplacian of network plus the identity to the -2. So you can see that the polarization is a function of 2 things. It's a function of the innate opinions, and it's a function of the network structure via the simple linear algebraic calculation. Something we're going to also care about is something we call disagreement, which is kind of like polarization, but actually kind of acts opposite to polarization. It's the sum of the squared differences of the expressed opinions across edges in the graph. So it's basically a metric of how much discordance is there between neighbors in the graph. Overall, over the whole graph, what's the sum of squared differences and opinions across the edges? So this nicely, like if I look at sum over all the edges of one expressed opinion minus the other expressed opinion squared, this is exactly the quadratic form of the graph Laplacian. This is exactly the expressed opinions transpose the graph Laplacian times the expressed opinions. And again, I can write it out in this relatively simple linear algebraic form using the Fredkin-Johnson equilibrium for the expressed opinion. Okay, and the final quantity that we're going to look at. Okay, so let me just say one thing. Generally, polarization and disagreement tend to counteract each other. Disagreement means that you have connections to neighbors with very different expressed opinions. And what that means is it kind of leads to smaller polarization because you're not just connecting to people with similar expressed opinions. It doesn't allow the variance of the opinions to get too large. So generally speaking, but it's not strictly speaking, polarization and disagreement we can think about as counteracting each other. Another quantity we're going to look at is the polarization and disagreement. This is literally the sum of the polarization plus the disagreement. And the nice thing about this quantity is that it's also given by a really, you can do a simple calculation to show that if I add up this linear algebraic formulation and this linear algebraic formulation, I get this linear algebraic formulation, which is really simple. It's the quadratic form of the innate opinions over the Laplacian plus the identity inverse. The main reason we're going to look at this is because we're going to use it as a surrogate for polarization. It often tracks the polarization, but it's a lot easier to get a handle on because it has a simple quadratic form. It doesn't have a squared term in it. So theoretically speaking, it's going to be useful to us, and it's generally going to track the polarization on the network. Okay, so now let me talk to you about the edge dynamics model. So what I just described was an opinion dynamics model on a fixed network and some measures of polarization that, given a fixed network and given a fixed set of innate opinions, those measures are fixed. So what we want to understand is, how does polarization evolve over time? And for that, we're going to have an edge dynamics model. So we're going to start with a graph that's at a Fredkin-Johnson opinion equilibrium, and we're going to modify edges via two very simple local update rules. The first type of edge modification is we're going to delete edges. And we're not just going to delete edges arbitrarily, but at every step, what we're going to do is we're going to pick a random edge to delete. And the probability that we delete it is going to be proportional to the disagreement across that edge. So basically the difference in expressed opinions of its two endpoints squared. And the reason we're making the probability proportional disagreement is this is modeling some very coarse notion of confirmation bias, the tendency of humans to seek out information that confirms existing beliefs. Or another way you can think about it is that you're more likely to unfollow somebody on social media if they're expressing very different opinions than your own. To counteract edge deletions, we're also going to have an edge addition model. And to add edges, what we're going to do is we're going to not take the opinions into account at all. We're just going to use a simple model for a recommendation system. So to add an edge, I'm just going to add a random friend-of-friend connection. So any edge ij such that I and j share at least one neighbor k. And this model is like a very simple, like who to follow recommendation system in a social network. And friend-of-friend recommendation systems have been studied a lot in the literature on looking at how do recommendation systems impact the structure of social networks. So that's the way that the edges are modified. We delete edges based on confirmation bias, and we add edges based on a simple recommender system. Note that this recommender system could have taken into account the opinions, but in our model, it doesn't. In some prior models, it does take into account the opinions. Okay, and just for simplicity, we're always going to add and remove the same number of edges. So the structure of our network is going to change over time, but the average density, the total number of edges, won't change. And also, this doesn't really matter, but for efficiency of simulation, we're actually going to add and delete edges in batches. Something like 5% of all the total edges will get added or deleted at once. And we find that the behavior of our model and the findings I'm going to present to you aren't super sensitive to this. So we can use fairly large batches and the behavior of the model doesn't change too much. So we just do this to be able to simulate the model efficiently. Okay, so just to give you the schematic one more time, we're going to alternate between two states in our model. And by alternating between these two states, our graphs and our opinions are going to evolve over time. And in turn, the polarization will evolve over time. So we're going to add and delete edges via these local update rules. Then we're going to re-update the expressed opinions to a Fredkin-Johnson equilibrium. And then we're going to repeat and then go back and forth. So let me just give you an example of this. And thanks to my student Adam for making this, this nice animation. I start with this graph. The colors represent the opinion. So maybe red is one extreme and blue is the other extreme. In my first step, I delete a random edge with probability proportional to its disagreement. So this edge would have a fairly high likelihood of being deleted because it's connecting two nodes with fairly different opinions. So let's say that's the edge I pick to delete. And then I pick a random friend-to-friend connection to add, regardless of what the opinions are. And then I update my graph. So after I cut that previous edge and I add that edge, I get two separate components in my graph now. After I do that, I rebalance the opinions to a Fredkin-Johnson equilibrium. So what you see is because that edge was cut, the opinions on the left side became much more consolidated around the red color. There's more polarization in the graph due to the loss of that edge. Let me just give one more example. We now repeat the process. So let's say we choose to cut this edge. This would have pretty high likelihood of being cut because a lot of the other edges are between fairly agreeable opinions. So these two edges would have a pretty high likelihood of being cut. So let's say we pick one of those edges. We add another random friend-to-friend. And then we're going to rebalance according to the Fredkin-Johnson equilibrium. So we now have this new graph that is even more polarized. We have sort of this clique of three nodes that have very blue opinions. We have this component of three nodes that's very red opinions. And then this one outlying node that is still connected to the blue nodes, but has gotten to more of an extreme opinion. Okay, so that's sort of what evolution of the graph looks like in our model. Let me say a couple, actually, any questions on that before I move on? Sorry, it's jumping all over the place a little. Okay, cool. I'll just mention a couple of other things which are a little bit less important, but one question when simulating our model is what should the initial conditions be? We typically initialize the graph when we start to either be a real world social network graph or a random graph, like an Erdős-Renyi graph or a Barabasi-Albert graph. We find that the behavior of the evolution process, like after a little bit of a burning period, isn't affected much by the choice of initial conditions. So we don't see drastically different behavior, whether we start with, let's say, a real world social network graph or something super unrealistic like an Erdős-Renyi graph. We always choose our innate opinions initially to be uniformly at random in -1 to 1, and we choose them independent of the network structure. It would be interesting to try out our model initialized, for example, on a real world social network graph with some notion of real world opinions that are actually correlated with the network structure. But for now, we're just going to have random initial opinions. These are the innate opinions, by the way, and they'll stay fixed. The innate opinions stay fixed throughout the whole process. The graph structure and therefore the expressed opinions are what change over time. And yeah, as I said, generally find that the initial conditions don't seem to affect the actual trajectory of our model all that much. Okay, and then the other thing I want to mention, one other thing that we do when simulating our model is that we typically choose a small percentage of the edges, something like 5 or 10% of the initial edges to actually be fixed and not subject to edge deletions. So I've colored those in like green here. Those edges just will remain fixed throughout the process. You can think about these edges as modeling connections which are not subject to deletion based on disagreement. So you can think about them as like connections between family members or coworkers, sort of social connections that are not going to be significantly impacted by opinion disagreement. But also they're just a useful thing in our model because adding a small percentage of fixed edges tends to lead to much more realistic network evolution, as I'll show you in a few slides. Without them, the graph tends to splinter into many different connected components corresponding to very tight innate opinion clusters. So basically polarization gets driven to a maximum and you don't see sort of like a realistic looking equilibrium graph. So by adding the fixed edges, we sort of prevent the graph from splintering into very extreme opinion clusters. Okay, so that's it. That's the model. We initialize a graph in some way. We update it according to Fredkin-Johnson dynamics and edge additions and deletions. We keep some edges fixed that we don't update, and then we see how does this graph, and in turn, how does the polarization evolve over time. So our main findings is that in conjunction, these confirmation bias and friend-to-friend recommendations tend to drive the network into a highly polarized state. But interestingly, and we were pretty surprised by this, if either is replaced by random control, then the network does not significantly polarize. So for example, if instead of deleting, this one is not surprising, if instead of deleting edges based on disagreement, we just delete random edges, the network isn't polarized just by friend-to-friend recommendations. And I think given that we start with initial random opinions, that is not too surprising. But what I found surprising is that if we have confirmation bias-based deletions, but then we just add random edges rather than friend-to-friend connections, we don't see a lot of polarization. It seems like the recommendation system is a necessary catalyst for the polarization to happen. We give some initial theoretical results explaining convergence in our model and explaining some of the phenomenon we see. Basically, we can analyze the effect of single edge swaps. And also we introduce a very simple surrogate model that allows us to look at how the polarization evolves over time. But these are very initial results. And I think a really great question is to get a better theoretical understanding of this model, or maybe even more simple versions of this model. And one thing we find is that at equilibrium, the networks produced by our model look somewhat realistic. They're somewhat realistically sorted by opinion. They have realistic triangle distributions and degree distributions, which we think is sort of interesting. And there's a lot of future work to be done on trying to validate the model against real world data, like looking at, for example, validating against data, like time series data of networks evolving over time. But at least some initial findings show that the model produces somewhat realistic looking social networks, even when you start from, say, like a Erdős-Renyi graph with random initial opinions. Okay, so finding one is that confirmation bias and recommendations are both necessary to drive polarization. So remember that in our model, edges are removed with a probability proportional to the expressed opinion disagreement. And if opinions are initially assigned at random, the key thing to observe is that the expressed opinions are initially very weakly correlated with the innate opinions. Basically, your expressed opinion is just a function of who you're connected to in the network, and your innate opinion only has a very tiny signal affecting that expressed opinion. So a priori, it's not really clear that these edge removals actually will lead to polarization. It's not clear that they'll lead to nodes with similar innate opinions being connected and drive polarization in that way, because these initial edge deletions at the beginning of the process are very noisy. They're deleting based on expressed opinion, but the expressed opinion doesn't necessarily correlate much at all with the innate opinions. And also, as I said, intuitively, friend-to-friend recommendations alone should not drive polarization, but they may enforce it, and that's what we find that they do. So let me show you a graph of basically the y-axis is our measure of polarization. That's the opinion variance over time. And time is just the number of iterations of our model. And I'm looking at two different graphs, an initial Erdős-Renyi graph and a real world social network graph. I think this was a subset of a Twitter graph. They don't behave very differently, but I just wanted to sort of illustrate that they behave similarly. If I have both confirmation bias-based edge deletions and friend-to-friend recommendations, that's these top two lines. I see that what happens is that polarization goes up pretty quickly before reaching an equilibrium at a pretty high value. If I have just confirmation bias, polarization does go up, and it kind of makes sense that it should go up a bit because I'm deleting these disagreeable edges, but it goes up very, very, very slowly, and it doesn't reach this equilibrium level of polarization. And I have just friend-to-friend recommendations, it basically doesn't go up at all, which is not super surprising. If I just have friend-to-friend recommendations and edge deletions are random, then I'm kind of ignoring the initial opinions in the evolution of my network. I shouldn't necessarily expect polarization to go up. And then the final example is that the final line, this dark line down here, is actually when I have both confirmation bias and friend-to-friend recommendations, but in a very dense graph. And I just want to include this example to point out that the graph structure does matter a bit. So here we have a very dense Erdős-Renyi graph. It's so dense that most nodes are friend-to-friends of most other nodes at initialization. So when that happens, the friend-to-friend recommendations become sort of useless. They're kind of the same as random edge recommendations. And in that case, you also don't see any polarization. So I just want to point out the network structure does matter. It needs to be sparse enough so that the friend-to-friend recommendations are actually meaningful and not just recommending random edges. Okay, so that's our first finding. Any questions there? Okay. One open question I think would be really interesting to tackle is, can we explain our findings theoretically? So it would be really interesting to show as an example type of result that I would love to get, but seems challenging. is that if I initialize our model with a sparse enough Erdős-Renyi graph and random initial opinions, show that confirmation bias alone would require, for example, exponential time to reach a highly polarized state. You would have to basically get lucky to remove all the right edges to get highly polarized. But show that with friend-to-friend recommendations, then you get convergence in something like polynomial time. Like show a gap between these two different models. I think it would be really, really cool to show this theoretically. We have some progress, but I think we're pretty far from showing that. And I think it would be interesting even in a simpler variant of our model. It doesn't necessarily need to be exactly our model. Okay, let me just show you sort of what the how the opinions change over time as this polarization occurs. So if I look at the initial state of the network, this is after the very first iteration. And by the way, the different colors in this graph are just different runs of the same trial. The opinions start with pretty high variance. They're randomly initialized between -1 and 1, uniformly at random. But because of the connections in the network in the Fredkin-Johnson model, they all sort of collapse down to the mean initially. Everybody kind of goes to the mean opinion because their neighbors are sort of randomly scattered throughout the network. They go down towards 0 opinion. Over time, the polarization tends to lead to bimodal or sometimes trimodal. It's not necessarily always bimodal polarization, where you get these two very distinct opinion clusters, and nodes tend to be connected to other nodes with relatively similar innate opinions. They're still driven towards the center. So you see there's very few nodes at the very extremes based on like the Fredkin-Johnson model, but there's these very clear two opinion clusters. And this graph on the bottom just shows you all the nodes. Basically, it's a line for every node in the network showing its expressed opinion over time. So remember, its innate opinion stays fixed, its expressed opinion changes, and we can see that what happens is that the expressed opinions sort of diverge out from the center as the network is polarized. Okay, so that's our main experimental finding. We also have some initial theoretical results trying to get a handle on what's going on in our model. The first result is understanding the effect of an edge swap. So let me just state what this theorem says. If I consider removing an edge E in my graph, E1, and adding an edge E2 in my graph, then the polarization plus disagreement, remember I said we're going to use this as a surrogate for polarization because it's easier to work through theoretically. I would rather this theorem said the polarization, but what we could prove is the polarization plus disagreement monotonically increases as long as the disagreement amongst the removed edges is significantly larger, or it's larger by an alpha factor, where I'll tell you what alpha is in a second, than the disagreement between the added edge. So basically, if I remove an edge that's relatively disagreeable and add an edge that's relatively less disagreeable, polarization plus disagreement increases. This is not a completely obvious fact because, for example, removing disagreeable edges can actually decrease polarization of the network at times. It's not like there's a strict relationship there. So this is a fact that we actually had to establish, and it kind of shows why our model should drive polarization in the long run, because at each local swap, we're trying to remove edges which are disagreeable, and then we're adding friend-to-friend connections, which should be more agreeable on average. Now, how much more disagreeable does it need to be? It needs to be more disagreeable by this alpha factor. Alpha is a function of the effective resistance across the edges in the graph, and I'm not going to go into the details there. But what you need to know is that alpha is upper bounded by a constant. So alpha is never more than like 3√3/4. But in well-connected graphs, alpha is usually very close to 1, as long as the effective resistances of the edges are relatively small. So you can think about alpha as being something like 1.2 or something very close to 1. Okay, so that's the effect of edge swaps. That kind of helps understand what's going on in our model at a local level. Note, by the way, I say that polarization monotonically increases, but I don't say by how much. So that's another thing that I would love to be able to show. But all we can say here is that, yes, it does increase. And I'll just mention that the proof of this is via these linear algebraic formulations for polarization and disagreement, and via Sherman-Morrison formula for rank 1 updates of the matrix inverse, which lets us understand how does the matrix inverse, and in turn, the polarization plus disagreement affect when you change when you add or remove edges. Okay, so I think this is a nice initial result, but I want to point out some significant limitations. First of all, it doesn't explain the importance of friend-to-friend recommendations, because both friend-to-friend and random edge addition should lead to edge swaps that increase polarization and plus disagreement. Because if I'm removing disagreeable edges due to confirmation bias, even if I'm just adding random edges back, the edges I add should be less disagreeable than the edges I removed. So our model it explains why in this graph, the slope is positive everywhere. Like, why does polarization go up everywhere? It explains why the slope is positive, but it doesn't explain why random edge additions have such a smaller effect on polarization than friend-to-friend additions. So it's really lacking in that regards, but it does at least explain why should polarization be going up. Another limitation, which I already mentioned, is that it applies to polarization plus disagreement, which is a decent surrogate for polarization itself, but we would rather have a result that applied to polarization itself. And it's kind of just a technical issue why we couldn't get it. It's because the linear algebraic expression for polarization is a little bit more complicated. Okay, our second set of theoretical results attempts to understand the behavioral model, not at a local, like single update scale, but more at like the evolution of polarization and disagreement over larger time scales. And the idea here is really simple. We're just going to replace our model with a super simple surrogate model. So given a graph and a mean zero expressed opinion vector, we're just going to do something really simple. We're going to divide the nodes in the graph into two groups based on the sign of their opinions. So all the negative opinions and all the positive opinions. And so let's keep thinking about my opinions as being real numbers between -1 and 1. I'm then just going to round the opinions to be binary. Anyone on the negative side is opinion -1, and anyone on the positive side is opinion 1. So I'm just literally rounded all the opinions to the edges of the interval. We let P be the fraction of in-group edges. So these are the fraction of edges that go between positive and negative opinions. We ignore how extreme the positive and negative opinions are. We just let P be the fraction of in-group edges. And we let Q be the fraction of out-group edges. Sorry, I said it backwards. So P is the fraction that go between either positive and positive or negative and negative. And then Q is the fraction that go between positive and negative. And then we just approximate our graph via an expected stochastic block model graph where every in-group edge is added with probability P and every out-group edge is added with probability Q. So what we basically do is we get rid of all the structure of our graph except for the in-group versus out-group connectivity, where I've defined groups in this very coarse way, who has negative opinions and who has positive opinions. And we use the fact that polarization and disagreement can be computed in a simple closed form for these expected stochastic block model graphs. So basically, the polarization in a stochastic block model graph is just some function of the size of the graph in the outgroup connectivity. And the disagreement is also just some function of the size of the graph and the outgroup connectivity. It's kind of surprising that these formulas don't depend on the in-group connectivity. There's sort of something weird at play where the stronger the in-groups, the more connections you have in groups, sort of, you'll have opinions that are closer within that group, which leads to like less polarization within the group, but then there's more polarization between the groups. So there's a sort of weird thing at play where the in-group connectivity doesn't matter. But anyways, there's nice formulas for polarization and disagreement in these stochastic block model graphs. And by the way, this Musco is not me. This is my brother, who had a paper about this a few years ago, I think at Wisdom, actually. Okay, so that's the surrogate model. And what we find is that this really simple approximation to polarization and disagreement that ignores all the structure in the graph except for in-group versus out-group connectivity does a decent job predicting sort of the evolution of polarization and disagreement in our model, and can explain the effects of several different parameters. It can explain how different parameters affect the evolution of polarization and disagreement. So just as an example, one parameter we can vary in our model, which I mentioned, is the percentage of fixed edges. So basically how many edges at initialization are not subject to the dynamics. It tends to be that as you fix more edges, the polarization reaches a less high value because there's more of these random edges that kind of keep the opinions close to each other according to Fredkin-Johnson dynamics. So that's sort of these lines in blue. And what we can see is that, like, well, actually, sorry, the colors are not showing up great, but at least that this theoretical model kind of predicts the fact that as you add more fixed edges, the polarization reaches a less high value. The other thing that it predicts is the big difference when you don't have fixed edges. So remember I mentioned when you don't have fixed edges, the network actually splinters. So what happens is something really interesting in terms of this disagreement. When the network splinters, the disagreement initially spikes because the network gets very polarized. We have lots of sort of divergent opinions, and the few edges that remain between these different groups lead to a very high disagreement. But then as the network splinters, the disagreement actually drops to zero because everybody's now disconnected from people with different opinions. So this is something we see only with 0% fixed edges. We see this huge spike in polarization and then this drop in disagreement. And this is something that's predicted by this really simple surrogate model. And I'll mention that if we do have fixed edges, kind of counterintuitively, both disagreement and polarization go up over time. So even though we're removing disagreeable edges, because the network's becoming more polarization, that actually drives up disagreement on average over time. It drives up both polarization and disagreement. And again, the surrogate model can predict that. So what's the takeaway from this? It's just sort of a nice way of understanding what's happening in our model. And it demonstrates that a lot of the network structure doesn't matter a ton, at least for the high level takeaways. For the high level takeaways, in-group versus out-group connection density is a key driver of polarization. All right, so I think I'm sort of like low on time, although I started a little bit late, so I'll try to wrap up pretty soon. Let me just say really quickly that our last finding is that our model tends to create relatively realistic looking networks at equilibrium. So regardless of starting conditions, the networks produced by our dynamics tend to display some hallmarks of real world social networks. So as an example, if we start with an Erdős-Renyi graph, the initial degree distribution of Erdős-Renyi graph is binomial. So it looks like a normal distribution, and it's very uncharacteristic of a social network graph. The steady state degree distribution after evolution looks much more realistic. It looks much more like a power law graph, a power law distribution that you'd expect to see in a real world social network graph. And for comparison, we kind of validated this graph against this Twitter data set. It has the same number of nodes, the same number of edges as that Twitter data set. And you can see that the initial versus the final, there's a big difference in the initial versus final degree distribution. The final degree distribution is much closer to reality. We find something similar with triangles. We see this very strong power law distribution in the triangles after applying our model to the graph. I don't think this is driven significantly by the opinion dynamics. It's driven a lot by the introduction of the friend-of-friend recommendations, which drives up the number of triangles in the graph. It means that the graph has really high clustering coefficient, which is characteristic of a real-world social network. But in any case, it's another example of how our model drives the initial network, even when it's something very unrealistic, like an Erdős-Renyi graph, to a much more realistic looking network. Okay, so that's our 3 findings. Let me just summarize and then mention a couple open questions. We proposed a very simple model of opinion and edge dynamics, basically a coevolution model between a graph and opinions to try to understand how does polarization arrive as the interaction between opinions and network structure. It builds on the established Fredkin-Johnson model, which lets us do some theoretical analysis and also simulate it efficiently. We find that both confirmation bias and friend-of-friend recommendations are required to drive polarization, and that surprisingly, just confirmation bias alone is not necessary. Is not sufficient. Thanks to our model's relative simplicity, it's tractable theoretical analysis, and we've obtained some theoretical results, although I think there's a lot more that can be done here. And finally, we find that our model is somewhat realistic and that it tends to drive the creation of networks with realistic social network-like hallmarks. Open questions, I think theoretically being able to more fully explain aspects of our model. So for example, why are the friend-of-friend recommendations so important? Or what's the density threshold for an Erdős-Renyi graph after which below that threshold, it tends to get polarized, but above the threshold, it doesn't. Why does the degree distribution shift to be more power law? Understanding all these phenomena in a theoretical way and being able to really explain them, I think would be really nice. Even if it wasn't like totally theoretical, but at least having a better explanation than we currently have. Another thing I'd be interested is understanding if you swap out the Fredkin-Johnson model for another opinions dynamics model, how robust are our findings to the underlying opinions dynamic model? And finally, it'd be very interesting to further evaluate the realism of our model. For example, if we could compare to real world data sets that have time series opinion data. So a record of how a graph changed over time and how opinions evolved over time. This type of data is really hard to get your hands on. Adam was working on a sort of a data set that was kind of giving us some results on basically congressional voting patterns. So you can infer opinions based on people's parties, and you can infer connection based on who they voted with over time. But in generally, it's pretty difficult to get your hand on this type of data. So I think it's a really good open question. And it goes beyond our model. Just how do you, in general, validate models of evolution of opinions over time? Okay, so thanks for having me. That's it. And if there's any questions, I'm happy to take them.
Let's thank the speaker. Questions? We have one question.
Hi, thanks for the great talk. So I have a clarification question. I think it was in finding number 1, like when you had the graphs both and just friend for friend. So my question is about the line of the just friend, like the one going out, the polarization going up slowly. So maybe I misunderstood something, but is it that although you're doing friend of a friend recommendation, you're not removing any disagreement edges, and that's why the polarization is not going up? Is that it, or did I misunderstand?
Yeah, so when I do, when I do just friend of friend, what the model is I remove a random edge from the graph, and then I add back a friend of friend edge. And actually polarization doesn't really go up at all in this model. It kind of stays flat. The graph gets more clustered, but the clusters aren't related to the opinion, so polarization doesn't tend to go up. When polarization goes up just a little bit, that model is I'm removing disagreeable edges, at least probabilistically, but when I add back edges, they're not based on friend of friend recommendations, they're just random edges. And it seems like because I'm just adding back random edges, the graph has trouble clustering, it has trouble sort of converging into a polarized state. It kind of remains at this relatively low level of polarization. Does that answer it?
Right, yeah, yes, thank you.
So this is the case, just confirmation bias is where it goes up slowly. In just friend of friend, it goes up not at all, or if it went up, it's just by luck.
Hi, Cameron. Thank you for the very nice presentation. This is Aris from KTA, Aris Gionis from KTH. So this is more like a comment.
Oh,
so you model confirmation bias as probability of an edge being deleted being proportional to the difference of the expressed opinions.
Right.
Then I was thinking that one could also model confirmation bias, probability of an edge being deleted proportional to the difference to some power alpha.
Right.
In that way, the random edge deletions will be for that alpha equals 0.
Right.
And then I was wondering if it is interesting to study what happens for that parameter alpha, if there is some threshold phenomena similar to Kleinberg's work on small world phenomena and so on. This is probably quite difficult.
No, that's a great question. I think we're a little far from understand. I mean, you could definitely study it empirically and maybe see if there's threshold phenomena. We're a little far from understanding it theoretically. I will mention that we did do it where alpha. So in all these results I showed you, alpha's 2. Well, as you said, just confirmation bias alpha 0. We also did it with alpha being 1. And it wasn't super different from alpha being 2. It was surprisingly close. But we didn't really explore it much beyond that. We honestly just did it because we were curious, but I think it's a great question to explore more.
We have another question.
Hi, Cameron. Thank you for the amazing presentation. My one question is basically, I'm still stuck with these innate opinions not changing over time, right? As the network evolution goes, after a person gets exposed to so much brainwashing, so to speak,
right.
At some point, he will have to jump out of the network, totally get out of Facebook or Twitter or whatever, or they will get adapting into those ideas, right? They're not going to sit there and wait to find friend and friend recommendations that will confirm their biases.
Yeah. I think, okay, so the bad answer to that is like, definitely the Fredkin-Johnson model is not totally realistic, and there's definitely an alternative opinion dynamics model. So we just wanted to start Fredkin-Johnson with it being simple. Maybe a little bit more of a in-depth answer is that you don't necessarily need to think about these innate opinions as actually being an innate opinion. They could just be something else that drives your opinion, an external force that drives your opinion that's not just the social network. So maybe the innate opinion is correlated with like where you live, or it's correlated with some aspect about your life which is independent of the social network. I mean, of course, maybe there's less and less aspects of your life that are independent of the social network, but you can just think about it as a driver of your opinion. That means your opinion is not completely determined by your friends in the social network. It doesn't need to be thought of as like some inherent belief you hold dear, if that makes sense.
Yes, thank you, Cameron.
Yeah. By the way, if you don't have an innate opinion, the model becomes de Groot dynamics, where you're just averaging opinions over time. And one issue with those types of models, the opinions just all converge to, they all just converge to the center opinion. So it's, yeah, anyways, you need something that kind of keeps the opinions from collapsing to the average.
Any other questions here in the Zoom call? Feel free to use the hands tool or write in the chat if you have any question. If not, I just have one question from the practical standpoint, industry standpoint, which is pretty alarming to see the velocity of disagreement and polarization in the surrogate graph that you were showing in there. So
Right.
from an industry standpoint, what could be done? Because maybe like the objective here is not to eliminate polarization, but to
Right.
mitigate that speed, that kind of sharp drop that you showed in there.
Yeah.
So what would be like any realistic effect on what you explained to mitigate that kind of velocity?
Right. I mean, I think it's a really good question. I feel a little bit qualified to answer it. I think maybe one thing to say is that I think one thing that's interesting is that friend of friend recommendations themselves are fairly benign sounding, right? They're not recommendations based on content. They're not trying to connect people to content that they agree with. It's just like the most basic form of a recommendation, like follow this person who it's exactly what Twitter and Facebook do all the time. Like, who do you follow? It's people who your friends follow, right? It's just collaborative filtering. So I think maybe the point is that what we're finding is that even this really benign sounding form of recommendations can have a really like catalytic effect on polarization, which I think is something that's worth exploring more. How do you prevent it from having such a catalytic effect? I'm not totally sure. I mean, of course, you could always say, don't do recommendations, just do random recommendations, but that wouldn't make sense to do if you're trying to increase revenue or increase engagement. So I don't think I have a great answer for you, but yeah.
Makes sense. Thank you very much. Let's thank the speaker again.